The universe is vast. Really, really vast. It's bigger than big, it's bigger than anything we can imagine. And it's filled with more stars than you could count in a lifetime. Actually, it's filled with more stars than there are grains of sand on all the beaches on Earth. That's a lot of stars. But the universe isn't just about stars, it's also about galaxies. Galaxies are huge collections of stars, gas, and dust, all held together by gravity. Our galaxy, the Milky Way, is just one of billions of galaxies in the observable universe, and each galaxy contains billions, even trillions of stars. It's mind-boggling to think about, but it's also incredibly exciting because the universe is full of mysteries. Mysteries that we are only beginning to unravel. Mysteries like black holes, dark matter, and the possibility of life beyond Earth. The universe is a cosmic spectacle. It's a place of incredible beauty and wonder. From the birth of stars to the death of galaxies, the universe is constantly changing and evolving, and we are fortunate enough to live in a time when we can witness these events firsthand. Thanks to telescopes like the Hubble Space Telescope, we can now see farther into space than ever before. We can see galaxies that are billions of light years away, and we can see stars being born and dying in real time. These images from space are not just pretty pictures. They are windows into the past. Because light takes time to travel, when we look at distant objects, we are seeing them as they were billions of years ago. This allows us to study the early universe and learn how it evolved into what we see today. For centuries, humans have looked up at the stars and wondered about our place in the universe. We've asked questions like, are we alone? How did the universe begin? And what is the fate of the universe? Today, we are closer than ever to answering these questions. We have a better understanding of the laws of physics that govern the universe, and we have more powerful telescopes than ever before. But there is still much that we don't know. The universe is full of mysteries that we are only beginning to explore. Dark matter, black holes, the Big Bang. These are just a few of the mysteries that continue to intrigue scientists today. So, where do we fit into all of this? As humans, we are just a small part of a vast and ancient universe. But that doesn't mean that we are insignificant. In fact, it makes our existence all the more precious. We are the only known species in the universe that is capable of understanding the universe around us. We are the ones who can look up at the stars and ask the big questions. And we are the ones who have the potential to unlock the secrets of the cosmos. Our journey to understand the universe is just beginning. But it's a journey that is full of wonder, excitement, and the potential for incredible discoveries. So let's embark on this journey together and see what we can find. Across the universe, hidden within vast clouds of gas and dust, lie stellar nurseries. These are the birthplace of stars where gravity acts as a cosmic sculptor, gently nudging particles together. Imagine a cloud of flour, so vast it could swallow 1,000 suns. That's a molecular cloud, and it's where the magic begins. Within these clouds, pockets of gas and dust begin to clump together. Gravity pulls more and more material towards these clumps, causing them to spin and heat up. Over millions of years, these clumps grow denser and hotter, eventually becoming protostars, the embryos of stars. These protostars are like celestial toddlers, still finding their footing. They're not yet stars, but they're on their way. They glow with heat, but not yet with the brilliance of nuclear fusion. As a protostar continues to gather mass, the pressure and temperature at its core increase dramatically. Finally, a critical threshold is reached. A temperature so intense, roughly 10 million degrees Celsius, that hydrogen atoms begin to fuse together, forming helium and releasing an incredible amount of energy. This is the moment a star is truly born. The energy released from nuclear fusion creates an outward pressure that balances the inward pull of gravity. The protostar, no longer just a ball of collapsing gas and dust, achieves a state of equilibrium and ignites, shining brightly for billions of years. This delicate balance between gravity and nuclear fusion is what defines a star's life. It's a cosmic dance, a battle of titans, with the fate of the star hanging in the balance. The life of a star is a story of balance, a delicate interplay between gravity and nuclear fusion. For millions, even billions of years, a star will continue to fuse hydrogen into helium in its core, radiating light and heat out into the cosmos. The size and mass of a star determine its lifespan. Giant stars burning bright and fast may live for only a few million years. Smaller stars like our own sun can live for billions of years, their slow and steady fusion providing a constant source of energy. Our sun, a yellow dwarf star, has been shining for about 4.6 billion years and is expected to continue for another 5 billion years. It's a comforting thought, knowing that our star, the anchor of our solar system, will continue to provide us with light and warmth for eons to come. As a star ages, it gradually consumes the hydrogen fuel at its core. Eventually, the core runs out of hydrogen, and the star's life enters a new phase. What happens next depends on the star's mass. For stars much larger than our sun, their end is a spectacular event, a cosmic explosion that can outshine entire galaxies. These massive stars, having exhausted their hydrogen fuel, begin to fuse helium and even heavier elements in their core, creating an unstable and increasingly dense core. This process releases tremendous amounts of energy, causing the star to expand significantly, becoming a red giant or even a supergiant. Eventually, the core of these giant stars collapses under its own gravity, triggering a supernova explosion. The star's outer layers are blasted into space with incredible force, scattering heavy elements, the building blocks of planets and life across the cosmos. After a supernova, the remnants of the star's core remain. Depending on the original mass of the star, these remnants can take on some of the strangest and most extreme forms in the universe. For stars similar in size to our sun, the core will collapse into a white dwarf, a small, dense object roughly the size of Earth, but with the mass of our sun. White dwarfs slowly cool down over billions of years, eventually fading into faint embers known as black dwarfs. If the original star was much more massive, the core's collapse can be even more dramatic, forming a neutron star. These objects are incredibly dense, packing the mass of 2 suns into a sphere only a few miles across. Neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. The most massive stars, those exceeding a certain critical mass, experience the most extreme fate. Their cores collapse completely, creating an object so dense that not even light can escape its gravitational pull, a black hole. Black holes are one of the most mysterious and intriguing objects in the universe, warping space and time around them. They are the ultimate cosmic abysses, where the laws of physics as we know them break down. The death of a star, whether it's a quiet fade or a spectacular supernova, is not the end. It's a transformation, a recycling of matter and energy that seeds the universe with the ingredients for new stars, planets, and even life itself. The cycle of stellar birth, life, and death is a testament to the constant evolution and renewal of the cosmos. Imagine looking up at the night sky and seeing not just individual stars scattered across the blackness, but vast, swirling clouds of light, each one containing billions upon billions of stars. These are galaxies, the fundamental building blocks of the universe, vast islands of stars, gas, dust, and dark matter all held together by the invisible hand of gravity. Galaxies are like cosmic cities, bustling with activity, with stars being born, living out their lives, and eventually dying, sometimes in spectacular explosions that seed the galaxy with the raw materials for future generations of stars and planets. Our own galaxy, the Milky Way, is just one of trillions of galaxies in the observable universe. Each galaxy is unique with its own size, shape, and history, but they all share a common origin, forming from the primordial soup of gas and dust that filled the early universe. Galaxies come in a variety of shapes and sizes, each with its own unique characteristics. The most common types are spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies, like our own Milky Way, are characterized by their graceful spiral arms, where new stars are constantly being born. These arms wind outwards from a central bulge which contains older stars and often a supermassive black hole at its core. Elliptical galaxies, on the other hand, are smooth and oval-shaped, with little gas and dust and few young stars. They are thought to be formed from the mergers of smaller galaxies, their stars moving in random orbits around the galactic center. Irregular galaxies, as their name suggests, have no defined shape or structure. They are often the result of galactic collisions or interactions, their stars and gas clouds thrown into disarray by the gravitational forces at play. Our home galaxy, the Milky Way, is a barred spiral galaxy, a vast city of stars stretching over 100,000 light-years across. From our vantage point on Earth, located about 2/3 of the way out from the galactic center, we see the Milky Way as a faint band of light stretching across the night sky. If we could travel outside the Milky Way and look back, we would see a magnificent spiral structure, with 4 major spiral arms winding out from a central bar-shaped structure. Our solar system resides in one of these spiral arms, the Orion arm, about 26,000 light-years from the galactic center. The Milky Way is home to hundreds of billions of stars, as well as vast clouds of gas and dust, the raw materials for new star formation. At its center lies a supermassive black hole, Sagittarius A*, with a mass millions of times greater than our Sun. This black hole, while invisible to our telescopes, exerts a powerful gravitational pull on the stars and gas clouds orbiting around it. Galaxies are not static islands in the cosmos, but dynamic and ever-evolving systems. They interact with each other through their mutual gravitational attraction, sometimes resulting in spectacular collisions and mergers. When galaxies collide, it's not like a car crash with stars smashing into each other. Instead, the vast distances between stars mean that direct collisions are rare. However, the gravitational forces at play can distort the shapes of the galaxies, triggering bursts of star formation as gas clouds are compressed. Over time, merging galaxies can coalesce into a single, larger galaxy, often an elliptical galaxy, with its stars moving in random orbits. Our own Milky Way is on a collision course with our nearest galactic neighbor, the Andromeda Galaxy. In about 4 billion years, these two spiral galaxies will begin to merge, eventually forming a giant elliptical galaxy. At the heart of most large galaxies lies a supermassive black hole, a cosmic monster millions or billions of times more massive than our Sun. These black holes pull in vast amounts of gas and dust, heating up as it spirals inward and releasing tremendous energy. Known as quasars, blazars, and radio galaxies, these active galaxies are among the most luminous objects in the universe. In the vast cosmic tapestry, galaxies are not just scattered randomly throughout space. They are organized into clusters and superclusters, forming a vast cosmic web. This web is constantly expanding, carrying the galaxies along with it. In the early 20th century, astronomers discovered that the universe is expanding. Distant galaxies are moving away from us, and the farther they are, the faster they recede. This expansion is a consequence of the Big Bang, the event that marked the beginning of space and time. As the universe expands, the space between galaxies stretches, causing their light to be redshifted. This redshift is key evidence for the expansion of the universe. The expansion of the universe has profound implications for our understanding of the cosmos. It means the universe had a beginning and suggests a future where galaxies become isolated. The ultimate fate of the universe is still a mystery, one that astronomers are actively trying to solve. Black holes. Just the name conjures up images of cosmic monsters lurking in the darkness of space, waiting to devour anything that strays too close. They are the ultimate cosmic abysses, places where gravity reigns supreme, where the fabric of space-time is stretched to its breaking point. For centuries, black holes were just theoretical curiosities, predictions of Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by the presence of mass and energy. But now, thanks to advances in astronomy, we have compelling evidence that black holes are real, and that they play a fundamental role in the evolution of the universe. Imagine a place where gravity is so strong that nothing, not even light, can escape its grasp. That's a black hole, a region of space-time where the gravitational pull is so intense that it warps the fabric of the universe, creating a cosmic trap from which nothing can return. Black holes form when massive stars, those with a mass several times greater than our sun, reach the end of their lives. As these stars exhaust their nuclear fuel, they can no longer support themselves against the relentless pull of gravity. The star's core collapses in on itself, becoming increasingly dense and hot. If the core's mass exceeds a certain critical limit, known as the Tolman-Oppenheimer-Volkoff limit, gravity will overcome all other forces, and the core will collapse indefinitely, forming a singularity, a point of infinite density and zero volume. As the core collapses, the star's outer layers are blasted off into space in a spectacular explosion called a supernova, one of the most luminous events in the universe. The supernova remnant, a cloud of expanding gas and dust, can outshine an entire galaxy for a brief period. Surrounding a black hole is an invisible boundary called the event horizon, the point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull, not even light. The event horizon is not a physical boundary, but rather a region of space-time where the curvature is so extreme that all paths lead inwards, towards the singularity at the black hole's center. Imagine you are an astronaut approaching a black hole. As you get closer and closer to the event horizon, you wouldn't notice anything special. You wouldn't hit a wall or feel any different. But to an outside observer, you would appear to slow down and redshift, your light stretched to longer and longer wavelengths as it struggles to escape the black hole's gravitational pull. What would happen to you if you were to fall into a black hole? Well, it wouldn't be pretty. As you approach the black hole, the difference in gravitational pull between your head and your feet would become increasingly extreme. This tidal force, caused by the difference in gravity's pull over distance, would stretch you out like spaghetti, a process aptly named spaghettification. Your body would be elongated and compressed, eventually being ripped apart into its constituent atoms. But don't worry, you wouldn't feel a thing. The spaghettification process would happen so quickly that your brain wouldn't have time to register what's happening. In fact, from your perspective, you would simply fall towards the singularity, unaware of the strange and violent fate that awaits you. Despite their name, black holes are not empty voids in space. They are incredibly dense objects, with a mass concentrated into an infinitesimally small region. And because they have mass, they have gravity. In fact, black holes have the strongest gravitational pull of any objects in the universe. As matter falls towards a black hole, it doesn't just disappear. Instead, it forms a swirling disk of gas and dust called an accretion disk. The material in the accretion disk heats up as it spirals inwards, reaching temperatures of millions of degrees. This superheated material emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. By studying this radiation, astronomers can learn about the properties of black holes, such as their mass and spin. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery. Black holes aren't completely black after all. Due to quantum mechanical effects near the event horizon, black holes emit a faint thermal radiation, now known as Hawking radiation. Hawking radiation is a consequence of the uncertainty principle of quantum mechanics, which states that it's impossible to know both the position and momentum of a particle with absolute certainty. Near the event horizon, virtual particle-antiparticle pairs are constantly being created and destroyed. Occasionally, one particle of the pair will fall into the black hole, while the other particle escapes into space. The escaping particle carries away some of the black hole's energy, causing the black hole to slowly evaporate over time. While stellar mass black holes, those formed from the collapse of massive stars, are impressive in their own right, they are dwarfed by the supermassive black holes that lurk at the centers of most, if not all, large galaxies. These supermassive black holes have masses millions or even billions of times greater than our Sun. They are thought to have formed in the early universe through the accretion of gas and the mergers of smaller black holes. Supermassive black holes play a crucial role in the evolution of galaxies. Their powerful gravitational pull influences the orbits of stars and gas clouds, shaping the structure of the galaxy around them. They can also trigger intense bursts of star formation and drive powerful jets of particles that can extend for millions of light years. For centuries, humans have gazed up at the stars and pondered a question as old as time itself. Are we alone in the universe? It's a question that has captivated our imaginations, fueled countless science fiction stories, and driven scientific inquiry for generations. The universe, as we're discovering, is vast beyond comprehension, filled with billions upon billions of galaxies, each teeming with stars and planets. The sheer scale of the cosmos suggests that it's highly unlikely that Earth is the only place where life has taken root. But finding evidence of extraterrestrial life, even microbial life, has proven to be an elusive quest. Yet the search continues, driven by an insatiable curiosity to know whether we share this cosmic neighborhood with other life forms. In our search for life beyond Earth, astronomers often focus on a region around a star called the habitable zone, or the Goldilocks zone. This is the sweet spot where conditions are just right, not too hot, not too cold, for liquid water to exist on the surface of a planet. Liquid water is considered essential for life as we know it, acting as a solvent for biochemical reactions and playing a vital role in the transport of nutrients and waste products within cells. Planets in the habitable zone receive just the right amount of energy from their star to maintain surface temperatures that allow for liquid water. Planets too close to their star would be scorching hot, their water vaporizing into space. Planets too far away would be frigid, their water locked away as ice. While telescopes have allowed us to discover thousands of exoplanets, planets orbiting other stars, searching for signs of life on these distant worlds is a formidable challenge. One approach is to listen for artificial radio signals, signs of a technologically advanced civilization. The search for extraterrestrial intelligence, or SETI, is a scientific effort that uses radio telescopes to scan the skies for these telltale signs of alien technology. The idea is that if an advanced civilization exists, it might be transmitting radio waves, either intentionally or unintentionally, that we could detect here on Earth. So far, SETI has not detected any confirmed signals from extraterrestrial civilizations. But the search continues with ever more sensitive telescopes and sophisticated data analysis techniques, hoping to one day pick up a faint whisper from across the cosmic void. In our search for extraterrestrial life, we often focus on finding life as we know it, life that requires liquid water, carbon-based molecules, and a source of energy. But what if life elsewhere has taken a completely different evolutionary path? What if there are forms of life that thrive in environments that would be toxic to us? Life that uses silicon instead of carbon as a building block? Or life that exists in forms we can't even imagine? Astrobiologists, scientists who study the origin, evolution, and distribution of life in the universe, are exploring the possibility of life as we don't know it. They are studying extremophiles, organisms that thrive in extreme environments on Earth, such as hot springs, deep-sea vents, and acidic lakes, for clues about the limits of life. Given the vastness of the universe and the likelihood of habitable planets, it seems we are not alone. Yet no evidence of extraterrestrial civilizations. This is the Fermi paradox, named after Enrico Fermi, who asked, "Where is everybody?" Many solutions exist, each mind-boggling. Perhaps advanced civilizations are rare, or Earth is unique. Maybe intelligent life destroys itself. Or advanced civilizations hide, observing us. Our search methods are limited, like ants searching for a flashlight. The Fermi paradox humbles us, reminding us of our place in the universe. From the birth of stars and stellar nurseries to the swirling galaxies scattered across the cosmos, we've journeyed through a universe more wondrous than we could have ever imagined. We've peered into the hearts of black holes, where gravity warps space-time and challenges our very understanding of reality. We've explored the possibility of life beyond Earth, searching for signs of other beings who might share this cosmic ocean with us. And what have we learned? We've learned that the universe is vast, ancient, and constantly evolving. We've learned that we are part of something much grander than ourselves, a cosmic story that began billions of years ago and continues to unfold to this day. We've learned that the laws of physics, while seemingly immutable, can lead to the most bizarre and awe-inspiring phenomena. Most importantly, we've learned that the more we discover, the more we realize how much we don't know. The universe is full of mysteries, puzzles that continue to baffle and intrigue scientists. Dark matter, dark energy, the Big Bang. These are just a few of the cosmic enigmas that beckon us to explore further, to push the boundaries of human knowledge. Our exploration of the universe is a never-ending journey, a quest driven by our insatiable curiosity to understand our place in the cosmos. Every new discovery, every tantalizing clue, only fuels our desire to learn more, to unravel the secrets that the universe holds. As we continue to explore, we must remember that we are not just passive observers. We are active participants in the cosmic drama, our very existence intertwined with the intricate web of cosmic processes that have shaped the universe we see today. The universe is our inheritance, a gift to be cherished, explored, and understood. It's a source of endless wonder, inspiration, and challenge. And as we venture further into the cosmos, we carry with us the hopes, dreams, and aspirations of humanity. So let us embrace the unknown, celebrate the mysteries, and never stop asking the big questions. For it is in seeking answers that we truly discover our place in the universe.